if you write a line of code, it does exactly what you tell it to do.
Right,
So
exactly.
it's a perfectly deterministic system. You input one thing, and, well, you expect a very specific output.
Mm-hmm.
So why is it that when a highly logical person tries to learn English, they suddenly feel like, I don't know, they're being forced to memorize this chaotic, completely arbitrary list of chores?
Yeah, it's frustrating.
It really is. So today we are taking a deep dive and basically tearing up the traditional grammar textbook.
Because, traditional methods, they really strip away the underlying mechanics of the language.
They really do.
They just hand you this massive list of rules and exceptions, and, well, they expect you to just accept them. But English syntax actually has this really elegant underlying architecture.
Oh, for sure.
If you look at it through the right lens, it functions incredibly similarly to a software engineering blueprint.
And that is exactly what we are getting into today. For anyone who has ever, hit a wall trying to construct an English sentence on the fly, this deep dive is going to act as your system diagnostic guide.
I love that way of putting it.
Yeah. We are exploring a set of sources today that treat English specifically through the subject-verb-complement structure, or the SVC structure, as we'll call it.
I like the SVC structure.
And the mission here is to completely rewire how you, the listener, look at states of being in English. We want to eliminate the guesswork and speed up how fast you can translate thoughts in your head.
To do that, we really have to look at the SVC framework as a state mapping engine.
Okay, a state mapping engine.
Yeah. The core concept to keep in mind as we go through this source material is this profound shift in perspective. You have to stop asking the traditional question, which is usually, what is the subject doing?
Right.
And you have to start asking, what property is being mapped onto the subject?
Okay, hold on. I understand the idea of mapping a property, but to really see why this SVC system is so different, we probably need to look at what we are comparing it against, right?
Absolutely.
Because the sources point out that beginners naturally gravitate toward a completely different structure, which is the SVO, or subject-verb-object pipeline.
Yeah, and there's a good reason for that. Human beings are biologically wired to track action.
Right, like survival instincts.
Exactly. If a tiger jumps out of the brush, you need to process that energy transfer immediately. So it makes total sense that our brains default to the SVO structure.
Great sense.
Think of SVO as an active data transaction. Energy in these sentences flows directionally, basically from left to right.
Okay.
Take the example from our sources. The programmer writes code.
Right, so the programmer, is literally an engine generating an action. The action is writes. And that, physical energy pushes forward to impact the code.
Mm-hmm.
It's a very active pipeline.
It is. The subject is actively doing work. But, language isn't just about things hitting other things. We also have to describe the static state of the world.
Which is where the SVC system comes in.
Exactly.
Yeah.
And it operates on completely different physics. The SVC system is entirely about identity and rendering.
Identity and rendering.
Yeah. In this framework, the subject is basically just an empty object node in a database. It does absolutely zero work.
I want to pause on that for a second because, honestly, my brain still wants verbs to be actions.
Oh, everyone's does.
Right.
Yeah.
Even when we aren't talking about physical movement, if I say the deployment was successful, the word was still feels like a verb to me. It feels like something is happening just because time is involved.
And that is the exact illusion that traps so many language learners.
Really?
Yes, we are completely conditioned to think that any word sitting right in the middle of a sentence must be an engine. But let's look at the actual physics of that sentence.
Okay, let's break it down.
The deployment is your empty object node. Was is not a power engine pushing energy at all. It acts as a logical bridge. It's a mirror. The property successful is simply being bound to the asset deployment.
So the deployment isn't performing the action of being successful?
No, not at all. It just is successful. The verb is merely a mirror reflecting that state back to the subject without any active motion whatsoever.
Wow. So it's literally just a static snapshot.
Exactly.
It's like setting an environment variable in a system. You were just saying deployment successful.
That's a perfect analogy.
And think about how much anxiety that strips away for you as a learner. When you are speaking, if you are constantly searching your mental dictionary for an action verb, you are going to freeze up when you really just need to describe a state of being.
Right. You get stuck looking for an engine.
Exactly.
Yeah.
But you don't need an action. You just need a bridge.
Which brings us to a really critical requirement of this whole architecture. If the verb is merely a static bridge, Well, the system has to be incredibly strict about the cargo that it allows to cross that bridge.
Ah,
We have to ask what data formats are actually valid to put at the end of an SVC sentence.
right. And in our engineering blueprint, this end slot is called the complement.
Yes, the complement.
And the
Okay.
sources are very, very clear that if you try to pass an invalid data type into this slot, your mental software is basically going to throw an error. The sentence will just sound fundamentally broken to a native speaker.
It will, because the compiler will only accept two specific data formats for that end slot.
Just two.
Just two. The first valid payload is the noun format. When you drop a noun into that slot, you execute what we call an identity map.
An identity map. Okay, let's look at the source example for this. Linux is an operating system.
Okay, so Linux is the subject node, is the bridge, and an operating system is the noun payload.
Precisely. And what is happening there is a total structural overlap. It is an absolute equation.
Right.
Linux equals operating system.
So they are the same thing.
Exactly. The subject and the complement are structurally identical in the database.
It's a pure one-to-one mapping, like renaming a file.
The file is the exact same thing, just with a different title. But we don't just equate things in daily conversation, right?
So of course not.
Sometimes we aren't just saying A is B. Usually we want to describe a characteristic. Like if I say, the server is fast. The server obviously isn't the physical embodiment of the dictionary word fast.
Right. And that requires the second valid payload, the adjective format.
Okay.
Instead of an identity map, dropping an adjective into the end slot executes a quality map. You're basically assigning a behavioral attribute to the subject's property register.
So I'm not saying server equals fast.
No, you're drawing an arrow from server to fast. You are mapping the quality onto the node.
Got it. So it's like adding a tag to a file rather than renaming the whole file.
That's exactly it.
This completely narrows down the English language.
Yeah.
If you are building a state sentence, you literally only have two options for the end of it. You either drop in a noun to create an equal sign, or you drop in an adjective to add a descriptive tag.
It is remarkably clean.
It really is.
And because the system strictly requires nouns or adjectives in that end slot, we can trace exactly why the system crashes so violently when beginners try to force an incompatible data type into it.
Oh, this is where we see that classic beginner bug.
Oh, yeah.
We see this all the time. Someone learns a rule, they try to apply it, and the sentence just shorts out. The sources highlight this specific error. It's saying the code looks beautifully.
Yeah, it looks beautifully. And, to a beginner, the logic behind that mistake actually seems completely sound.
Because of the ly rule.
Exactly. They have been taught in their textbooks that looks is a verb, and adverbs, words that end in ly, are used to modify verbs.
Right.
Therefore, beautifully should be correct. But to understand why it fails, we really need to run a diagnostic trace on the syntax.
Okay, let's run the trace. Step one is the verb mode check. Right.
Right. We scan the verb looks, but think about it, the code itself doesn't have biological eyes.
No, it doesn't.
It isn't performing a physical action of looking around the room.
Right, so the system registers looks as a linking verb. In our framework, it is a sensor wire, not an active action chip.
Which triggers step 2, the data flow trace.
Okay.
Because looks is a sensor wire and not an active engine pushing energy to the right, the data pipeline actually flows backward to modify the subject, the code.
The energy flows backward. That is like a massive visualization shift.
It changes everything.
Because active SVO sentences push forward, but state SVC sentences flow backward to reflect on the subject.
Exactly. And then we hit step 3, the payload validation check.
Okay, what happens there?
Well, the system inspects the input beautifully, which is an adverb. By the fundamental rules of the language hardware, adverbs can only describe how an action is performed.
But since the code is a static noun, and we just established it isn't physically using eyes to perform an action.
The system rejects the adverb.
Right, because there's no action to modify.
It is exactly like trying to plug a USB cable into an HDMI port.
Oh, that's a good way to look at it.
Yeah, they might both be cables, but the slot expects a physical description, an adjective, while the adverb is trying to describe an action that doesn't even exist. Since there is no action happening, the compiler throws a type mismatch error.
The wire is just reporting a visual state, so it strictly demands an adjective. It has to be, the code looks beautiful.
Yes, beautiful, no ly.
Once you realize that this end slot is strictly dedicated to defining the static subject, you stop accidentally loading adverbs into it. You literally can't perform an action beautifully if no action is taking place.
And that is the power of understanding the architecture rather than just guessing what sounds right. You are validating your data payloads against the system.
Yeah.
And understanding this prickward flowing sensor wire concept really opens the door to scaling the system up significantly.
Because linking verbs aren't just limited to is and are, right? The mapping system has a lot more channels than just the verb to be.
Oh, absolutely.
The sources actually outline this really cool master configuration matrix for the state mapping engine. And it has 3 distinct mapping vectors.
Let's walk through them. The first vector is what we have been discussing mostly today, the pure identity map.
Okay.
This uses your core linking verbs like is, am, are, was, were. The system output target here is just to establish absolute parity between the subject and the payload.
Right, like our earlier equation. Git is a version control system.
Yeah.
Absolute parity.
Yes. Now, the second vector in the matrix relies heavily on those sensor wires we just diagnosed. We call it the telemetry map.
The telemetry map.
Yeah, this channel uses sensory verbs, words like look, sound, feel, taste. The payload here is typically an adjective, and the system output is to feed sensory attributes back to the subject.
Oh, like a probe sending data back to headquarters.
Exactly like that.
So if I say, the document sounds professional, the document obviously isn't actively using ears to listen to anything.
No.
The word sounds is just a sensor wire feeding the attribute of professional backward onto the document.
You are just reading the system telemetry. The human interface with reality relies heavily on these sensory feedback loops.
That makes so much sense.
But, states aren't always permanent. A server might be fast today and, well, painfully slow tomorrow.
Too true.
Which requires the third vector, the transition map. This uses verbs like become, turn, get.
Okay.
The system output target here is to track dynamic state changes over a timeline.
So like the example the sources use, the logs became massive overnight.
Right. The logs didn't perform an action.
They just grew.
Their state simply updated.
Yeah.
So we use the transition vector became to map the new adjective payload massive onto them.
When you look at an English sentence this way, instead of memorizing a massive list of random vocabulary rules, you literally start to see the logical channels.
You really do.
We see the mapping directions. You know exactly what kind of structural cable goes where.
It builds a highly reliable communication stack. But I will say, even with a reliable stack, if you misunderstand the core operating modes, you can still cause a massive structural collision.
Oh, yeah. And there's one specific error beginners make that basically crosses the wires between the 2 isolated systems we have discussed today.
The action system, SVO, and the state system, SVC.
Yes. If you have been learning English for any amount of time, you have likely either made this error or heard someone else make it. Let's bring up the infamous phrase from our sources.
Yeah, I agree with this choice.
I agree. When a native speaker hears that, the sentence essentially shorts out in their brain.
It really does, but why?
We have to look at the root cause. The word agree is already a fully functional action chip. It is a verb that outputs its own forward execution current.
Right.
So it belongs in the active SEO pipeline.
Right, I agree. The action is actively happening.
But look at what happens when a beginner places am in front of it. Am is a core vector for a pure identity map.
It's an equal sign. Yes. So you are literally trying to compile the equation I equals agree.
You are trying to force an active action chip into a static state slot.
Exactly.
You essentially have 2 verbs fighting for the exact same socket. You can't, plug an engine into a mirror socket.
No, you can't. And the sources note this is the exact same reason why people incorrectly say, I am like Python, when they really just mean they enjoy the programming language.
Oh, I've heard that one too.
Because like is the action chip. By saying, I am like Python, you are running an identity map saying you, the human, are structurally identical to the Python coding language.
Which is obviously not what they mean. So how do we patch this bug? If someone finds themselves constantly crossing these wires, what is the fix?
The patch basically requires you to make a definitive choice. You must choose one operating system, mode, action, or stated engine, and keep them completely insulated from each other.
Okay, so they can't mix.
Never. If you want to use action mode, you must delete the equal sign. Remove the static bridge.
So the clean operation is simply, I agree with this choice. The energy flows cleanly from the subject through the action of agreeing to the choice.
Now, if you want to express this using state mode and you decide to keep the equal sign I am, You must convert the action chip into a valid state payload.
Okay.
You literally have to change the verb into a noun property, so it becomes, I am in agreement with this choice.
In agreement is the noun payload.
Exactly.
So the equation becomes I equals a state of agreement.
Wow. Both options are perfectly valid English, but they run on completely different hardware systems.
That's the key. Keep your states clear and always validate your payloads.
This has been so eye-opening because, knowledge is most valuable when it is understood systemically and applied correctly.
Absolutely.
By keeping your action and state systems insulated from one another, and by rigorously validating your data payloads to ensure you aren't, plugging adverbs into static sockets.
Right, checking those cables.
Yeah, and by understanding the backward flow of those linking sensor wires, your English compilation becomes vastly faster and just so much more professional. It really takes the fear out of speaking, I think.
It totally does.
It shows that critical thinking and pattern recognition are your best tools.
Mm-hmm.
Finding these patterns, like treating verbs as mapping vectors or sensory telemetry wires, it turns the overwhelming process of language learning into this elegant, highly predictable system.
You go from being a frustrated student to a language engineer.
It allows you to actually see the architecture of English.
Yeah, it does. Well, before we log off, I want to leave you, the listener, with a final provocative thought to explore on your own.
Okay, let's hear it.
We've spent this entire time talking about how the English SVC system maps properties onto subjects. We've mapped out the equal signs and the sensor wires.
Yeah.
But think about your native language for a second. Think about your mother tongue.
Mm-hmm.
Does your native language use these exact same equal signs and sensor wires in the exact same way?
Mm-hmm.
Or is your mental hardware running a completely different core operating system?
Oh, that raises a brilliant question about how we actually translate concepts in our heads.
Right. So next time you speak in your native language, try to actively spot the structural collisions you might be making when you translate back and forth. Are you trying to plug an English action chip into a state socket from your native language?
It's a great exercise.
Because once you can visualize the blueprint of your own language, mastering the blueprint of another becomes nothing more than a simple system upgrade. So keep analyzing those blueprints, keep checking those wire connections, and never settle for just memorizing the rules when you can understand the engineering behind them.